Okay, so I have the pleasure of introducing our final plenary speaker today, Professor Nick Wormald. Professor Wormald is an Australian Laureate Fellow of the Australian Research Council and professor at Monash University, professor at the School of Mathematical Science at Monash University, Melbourne, Australia. He's actually just joining Monash. He was for several years at the University of Waterloo as a Canada Research Chair in Combinatorics and Optimization. So his areas of expertise includes combinatorics, graph theory, random graphs, enumeration of graphs, maps, and combinatorial structures, probabilistic combinatorics, and he has incursions into real applied mathematics of underground mine optimization. So he is very respected in the area, and he is in fact an editor-in-chief of journal Combinatorial Theory Series B, which is one of the most prominent journals in the area. So today Nick will speak about random graphs. So let me just mention two of his contributions to the area. So he introduced what is now known as the differential equations method, which is used by several researchers, and it has been very important in establishing fundamental results, both in random setting and also in the deterministic settings, such as Ramsey theory. Over 20 years ago, he gave a very nice solution to a Hamiltonicity problem of random regular graphs. And in that work, he introduced what is called the small subgraph conditioning method. So Nick has Brazilian connections. He just visited Porto Alegre. He visited his student, PhD student, who finished at Waterloo a few years ago. And I'm happy to say that his ties are getting stronger. So a student of his, a Brazilian student, will defend her thesis in a couple of weeks at Waterloo. And right, so I just hope that this tie will strengthen. Today, Nick will talk about random graphs, random regular graphs, and combs.
Well, thanks for the elaborate introduction, and thanks for the invitation to speak here. And thank you, everyone, for coming. So, random graphs, random regular graphs, and combs, I'll explain those words in the rest of the talk. Now this thing should work, yeah? Is it on? That part works, this part doesn't. Which one? One?
I think
it is, it's working, yeah. Great. It does work in theory and in practice. Okay, so in the beginning, according to legend, random graph theory started with two papers of Erdős and Rényi in 59 and 60. They introduced a model of random graphs, but quite quickly two models were being looked at, called GNP and GNM. In GNM, that's the one that Erdős and Rényi looked at. So you look at a set of vertices and or points, and just take a random graph with m edges on that set. So just to make sure you know what a graph is. Here's a set of 8 vertices, and this is a graph on those vertices. A set of edges, pairs of lines joining the points. Each edge, in this model, in the GNM model, each graph with m edges is taken with the same probability. In GNP, that's a different model where you just start with the vertices and you put edges one at a time at random with probability p each, independently. Now, Erdős and Rényi, as I said, looked at the GNM version, but there's a strong relation between these two models. GNP looks very much like, a random graph from GNP looks very much like GNP. GNM, where m is asymptotically n choose 2 times p. So if you prove something about one of these models, there are some general theorems that will often tell you, well, that result also holds in the other model. The m here is, of course, the expected number of edges in the GNP model. So maybe that's not too surprising that they're similar graphs, similar models of random graphs. Now, that statement is true for so many properties. It's true for just about everything I'm going to talk about in this talk, to the extent that I'm going to talk about results that were proved for GNM, but I'm going to just say they were proved for GNP. And so I'll put everything in terms of GNP for easy comparison. And the translations all exist. So in their work, there were two major features that got looked at and actually people got excited about and still get excited about, which are basically the phase transition and threshold functions. So in this talk, I'll try to give you an idea of what these things are, although maybe you already have some idea. And also, I'll try to give you an idea of why random graph theorists can still get excited about these things. Along the way, I'm going to also introduce random regular graphs. So actually the graph back here. So this graph has every vertex of degree 3. Every vertex has 3 edges coming out of it. So it's a 3 regular graph. And if we take a random graph with a random regular graph or deregular graph and take each one with the same probability, that's a nice probability space, which it turns out that'll occur. It'll turn up in my discussion of the phase transition and in threshold, and in work on threshold functions as well. And to tie it all together, I'll talk about this conjecture called the comb conjecture. So, by the way, random graph theory has many applications now in the time since Este and Rani started. I want to point out, in case you've noticed, that the use of methods and results in random graph theory has actually been expanding a lot in the last 60 years, 50 years or so. So first of all, phase transition. What's a phase transition? Something changes fairly suddenly in nature. So Este and Rani looked at this giant component in a random graph. So you look at a random graph with edge probability p. Now, we're going to be looking at things where the p is a function of n, and n goes to infinity in order to get interesting results. If p is c over n, where c is a constant less than 1, then a random graph looks something like this. Lots of little pieces scattered. The largest component has size order log n. This sort of thing Este and Rani derived in those two papers. After the phase transition, something's happened by the time, if c is greater than 1, a constant greater than 1, and you look at a very large n, look at what the random graph looks like. Well, it looks like this. There's a big connected piece. Now, connected means there's a path between any two vertices along edges. And the rest of the graph actually looks like a random graph as it was before the phase transition. The bigger c gets, the bigger this connected piece gets, and the sparser the rest of it gets. Now, the fact that there's one big piece and the rest are basically smaller, a lot smaller, that was shown not just for constant c, but when p is c over n, if c was, well, p is now 1 plus epsilon over n, where epsilon is going to 0. As long as it goes to 0 faster than n to the minus 1/3, then we get basically this picture, but the giant is much smaller. It's now size little o of n, but it's still much bigger than all the other components. And actually, if you think about this n to the minus 1/3, that the different models of random graphs often have this n to the minus 1/3 thing coming up. So this is like a universality class that's basically a mystery. Why is it always n to the minus 1/3? Yeah, so we know there's a giant component after when p is growing substantially above 1 over n, but still asymptotic to 1 over n. Well, the next question is, how big is the giant? Este and Rani answered this when p is like constant over n. Just in case you're not sure about what a giant is, it's not that sort of giant. We can try to measure it with a ruler, but of course that won't work in our case. What do we do? Well, we have to do a lot of other computations. So it took quite a while for Bolobash and Woodchuck to other people were looking at this, but eventually Woodchuck finished off the whole range of p's in this supercritical range. Bolobash obtained this result for a restricted range of p. So in the whole supercritical range, where the epsilon is much bigger than n to the minus 1/3, I've just stated the result for epsilon being little o of 1, but we know the result when epsilon's constant as well. Then the giant has asymptotically 2 epsilon n vertices. For once, I'll state what happens in GNM, just out of interest. If the number of edges in the random graph is n over 2 plus s, and s is much bigger than n to the 2/3, then the giant component will, with high probability, have asymptotically 4s vertices. So that's the first question: how big is it? The next question is, that tells you how big it is with a high probability, but what's the distribution of the size of the giant look like? Is the giant always that big, or is it sometimes rather small? How large is the variance of the size of the giant? And what's the shape of the distribution? So Stepanov determined the variance and showed it's asymptotically normal for p basically a constant times n, where of course the constant has to be greater than 1. It was actually surprising a long time before we got this thing for the whole supercritical range. So whenever that giant occurs, if epsilon's growing faster than n to the minus a third, then we get, again, normality, and we know what the variance is. So asymptotically normal size. And I just for a minute want to say something about our argument. This is an argument that I gave with Boris Patel, and it tells you quite a lot of other things as well. So there's the giant. We want to say basically the variation in the size of the giant. So if we look at the giant, what we actually do is look inside the giant. Now, there are other people who prove things about these giants by looking at what the rest of the graph is and deleting it, looking at how big the rest of the graph is and deleting it. In fact, that was basically, I think, one of the first arguments. But we look inside it, and inside you can see what actually is technically called a core and a mantle, just like in Ingrid's talk on Monday, looking at the Earth. And what the mantle is a set of trees. Trees are graphs with no cycles, attached to this core thing. Well, what the core is the maximal subgraph that doesn't have any trees attached. So it's actually the largest subgraph where the minimum degree is 2 or bigger. Now, well, the core had been looked at before a little bit, but not too much had been done with it. But some things have been done with it, and we found it handy to look inside the core. When you look at the core, you can consider the vertices of degree 2 and vertices of higher degree. And if you look at the vertices of degree 2 and just sort of pretend they're not there and replace those paths by edges, then you get what's called the kernel, where every vertex has degree at least 3. Now, why might you want to do that? Well, actually, because it turns out that we can... Now, the approach that Patel and I had is one of involved some enumeration. Basically, we were saying how many of these structures there are. But in order to prove how many connected structures there are like this, we actually looked at the random structure. And we know a lot about random kernels. So this is a random graph subject to minimum degree at least 3. In this case, I've drawn the kernel with every vertex of degree exactly 3. Well, it turns out in part of the interesting supercritical range, where the giant is only just growing, it's just fairly sparse. At that point, the kernel will, with high probability, have all vertices of degree 3. So by looking at the structure of these things and some enumeration results and random results, we basically counted these and counted how many ways you can attach all these trees on the outside in the mantle. And using all that, we were able to talk about the distribution of the size of the giant in GNP. Actually, the approximate structure of the kernel was already known in some sort of more approximate sense. That was used by Woodchuck, and facts about random kernels, which in this case is a random 3-regular graph. Those were used in order to prove things like, by Woodchuck, to give a bound on the length of the longest cycle, and a lower bound on the length of the longest cycle in the kernel. He actually used a result that wasn't proved yet, but that's all right because we proved it not long after. By the way, a much more precise model than Woodchuck's was given recently by Ding, Kim, Lubetsky and Perez. They actually used the much more precise enumeration results that Patel and I obtained. And now that you have a model of a giant component which consists of starting with a random kernel with certain description and then sticking in vertices of degree 2 along the paths, using certain rules, certain random processes, and growing the trees, and there you have your random giant. So you can prove lots of things about it knowing the parameters of this model. Okay, so that was the quick course on the phase transition. What we've been doing lately is focusing on some of the supercritical giant properties. For threshold functions, so this was actually more in the first of Erdos and Rainier's papers. Now, one bit of terminology, if I mention a graph property and you're talking about probabilities, you can just equate the property with the set of graphs that have that property, and that set has a probability in any graph probability space, and so we can talk about the probability of properties that way. That might sound rather trivial, but it just, for instance, with the property of has a component of at least n over 2 vertices, that is a property which, this large component question, which I've already talked about. Basically, it's a question of how big is a giant, and they looked at that in their second paper, actually. Other properties of the sort of the degrees of vertices, or having no vertices of degree 0, or being connected, they were looked at in the first paper of Erdos and Rainier. But many, many other properties have been looked at, of course, for random graphs. Now, one of their earliest results was that when p is a constant times, well, a function times log n over n, so the graph is fairly sparse at this point. In fact, the average degree is around log n. There are about log n edges incident with any vertex. And basically, that's the point at which the random graph becomes connected. So there's a pass between any two vertices. If the alpha here goes to 0, then the graph basically won't be connected, and if alpha goes to infinity, then it's connected. Well, they proved much more precise results than this, especially in their second paper. But this is enough for us to say that log n over n is a threshold function for this property. So all we need is the p to be alpha of n times some function. Then that function is the threshold function as long as the property behaves this way, as alpha goes to 0 or to infinity. So they showed this as they also showed this threshold for the property of having no vertices of degree 0. And actually having no vertices of degree 0 is a prerequisite for being connected. Now, some thresholds are very sharp, what we call sharp. So if you look at the property of having a subgraph of minimum degree at least 3, so there's a subgraph in there somewhere, it might be a big one. In fact, the first one that appears is actually very big, constant times n size. All vertices are degree at least 3. That has a sharp threshold. There's a constant which we know, it's approximately 3.35 divided by n. So the average degree is 3.35. The p is, if p is 1 minus epsilon times this function, then the probability is basically 0 of having such a subgraph. And if it's 1 plus epsilon times this function, then the probability is 1. That's for any epsilon greater than 0. So that's called a sharp threshold because of that epsilon feature. Here's a non-sharp threshold containing a cycle. There's no sharp threshold because the probability goes smoothly from 0 to 1 over some range, some constant range. If p is a half over n, then the probability is positive for large n. Okay, so this might be a little bit surprising when you consider that it contains a cycle. That property is equivalent to having a subgraph with minimum degree at least 2. It's equivalent, deterministically equivalent. So the difference between subgraph of degree at least, min degree at least 2 and degree at least 3, one threshold was not sharp and the next one's sharp. The question of which thresholds are sharp actually has been studied quite intensively in the last 15 years, and there are some very quite deep results by people like Friedgut and Bourgain giving results, but there are still some very mysterious questions there, some conjectures that are not answered. But for this talk, I want to move to really a simpler question of when is there a threshold? So for a threshold, you need a function alpha that if it goes to 0, then the property doesn't hold, and if it goes to 1 to infinity, then the property does hold with probability 1. Balabash and Tom. Well, if you're going to talk about such a thing, then actually then it makes sense to talk about monotone properties. So you basically want to make sure that the probability increases as p increases. And if a monotone property is one such that if I have a graph with the property and I add an edge, then the property is still holds. So for instance, if the graph's connected and I add an edge, it'll still be connected. So connected is monotone. Okay. And Balabash and Thomason showed with a very easy argument that if a graph's monotone, then there's a threshold function. I'll say easy because it's well, it's easy for me to explain exactly what the argument is. And I'm going, or at least sketch it. I'm going to do this because it's something that I'm going to tell you about or use later as well. It comes into quite a lot of arguments, this idea, in random graph theory. So the idea is, first of all, choose a p0 such that the probability that the graph has the property is some positive epsilon. Now, as long as this property is not trivial, there's always going to be such a p0. Now, take k independent copies of the same random graph Gn p0. So we're thinking of them with the same vertex set. You have the same vertices and you randomly take k of these graphs, and then take a union of them, so you just put them all one on top of the other. Now, when we take the union, it's easy to prove that that's distributed as another random graph, Gn p1, where p1 is at most k p0. p1 would be the same as k times p0 if you knew that none of the edges ever coincided between the random graphs. It's sort of like the extreme case. Now, doing this is called k-round exposure. You generate a random graph Gn p1 by taking k sparser random graphs and putting them one on top of the other. It's also called sprinkling in some places, that sort of thing. Now, elementary calculations tell you that Gn p1 has a probability q with some property q, with a probability that's close to 1 as long as you take enough copies of the random graph. And that's an easy calculation. Well, that's easily seen, I think, because this is a monotone property. So if G1 has a property, then the first random graph has a property, then the union will have it as well. Same for all the others, and they're all independent. So if you take enough copies, you'll eventually get the property you want. Okay? So now what we have then is by taking p0, the probability was some small epsilon, and by taking a large constant multiple of p0 at most, then we get probability 1 minus epsilon. And that's basically the situation that you can use to show that there's a threshold. Okay, so there is a threshold for the property Q. The problem is we don't know where it is. This proof gives no information on where the threshold occurs. At what p does the threshold occur? So a property, as I said, is a set of graphs. So we can ask, when does a certain subgraph appear in a random graph? We can describe a sequence of graphs indexed by n, and we can ask, for what n does a random graph GNP contain one of these things? Or what's the probability it occurs? So we've answered this question for, say, general class of graphs like connected graphs. Connected graphs appear when the p is around log n over n. But we can pick out one graph for every n and ask, when does it occur? In particular, a lot of attention's been given to spanning trees. They're quite simple graphs, but there's a lot not known about this. So there's a graph. You might recognize it. And this is a spanning tree of that graph. So it's a connected subgraph with no cycles, and in fact, it looks like that. And so that's called a spanning tree, as long as it contains all the vertices of the graph, the original graph. And these things of degree 1 are called leaves, of course. I'm going to refer to those in a minute. To have a spanning tree, of course, our random graph would have to have minimum degree at least 1. All vertices need to have degree at least 1. And that doesn't happen for GNP until, the P is log n over n, basically. So the conjecture, which no one seems to know where it came from, is that GNP, the random graph, contains actually copies of all n-vertex trees as long as there's some upper bound, if you restrict to those trees with a given upper bound on their degree. It contains all of them when P is some constant times log n over n. And the constant may depend on that upper bound. So this is getting at the question of what the threshold is for the appearance of a spanning tree. So we know that they don't occur until P is at least constant log n over n, and the conjecture is that actually soon after that they do occur. At least the ones with a bounded degree. Now this is known, there's an old result I have with Bender that says that almost all trees satisfy this conjecture. That's almost all of them in some sense. When n's large, the proportion that's satisfied contains almost all the trees. It's been proved recently for all trees with constant n leaves by Alon Krivelovich and Sudakov. In some sense, they don't actually prove that the graph contains all of them simultaneously, but they can pick one tree for every n, for every number of vertices, and the probability that tree is contained in GNP tends to 1. So these trees require a lot of leaves. But, so there are still mysteries about trees. For arbitrary subgraphs, we can ask the same thing. When does an arbitrary subgraph occur? Well, we get a clue, of course. The first thing you ever do when you're asking about something in random graph theory is ask, what's the expected number of these things? So let xh be the number of copies of the subgraph you're interested in. So this subgraph h, it's indexed by n. So for every n, I give you a graph, h of n, and then I ask about the probability that h of n is contained inside GNP. P also is indexed by n. It's a function of n. So let's say the appearance threshold is that P such that when we compute the probability that the random graph contains the graph we're interested in, that probability is exactly a half. Since as P goes from 0 to 1, of course, the probability will go smoothly from 0 to 1, so there should be a half somewhere. Now, Markov's inequality tells you immediately that the appearance threshold cannot be any smaller than the minimum P such that the expected number of copies is at least a half. In other words, if it has probability a half of appearing, then you've got to, on average, have at least half of one there. Okay. So our first guess for where the appearance threshold might be could be around the same value of P, where you expect on average half a copy. Or maybe one copy you could get. It should be around the same place. On average you get a copy. Then the probability it occurs maybe should be around half. Well, this fails badly because of what I'll call non-homogeneous graphs that are not very balanced. If a graph has bounded size, first of all, there's this nice little formula for the expected number of, if f is fixed, say, a fixed graph, the expected number of copies of that graph in our random graph GNP has this little formula where we're dividing by the number of automorphisms of the graph, which is fixed, it's a constant. So you get that when P is around, when the numerator is around 1, So P is around n to the minus number of vertices over number of edges. At that point, the expected number of copies that's where the expected number of copies will be a half, somewhere around there, for that value of P. And you can just use that on this graph. Suppose this graph is called a K4, the 4 vertices here, all joined to each other, and there's a tail of length 4. Look at the point where the expected number reaches a half, and the P will be constant times n to the minus 4/5. But if you look just at the K4 part and do the same computation, the expected number of those is a half when P is around n to the minus 2/3. Well, by the criterion that the appearance threshold cannot be any earlier than this point here, where the expected number reaches a half, you cannot get the K4, the head of this thing, appearing with probability half until P is this big, n to the minus 2/3. And that's actually a lot bigger than n to the minus 4/5. So the appearance threshold for the whole graph can't beat where the head appears, which is n to the minus 2/3, much bigger than the place where the expected number of copies of H is a half. So something is not appearing, it can't appear yet because it needs a denser part to appear first. So that means that the expected number doesn't tell you much really about the threshold of appearance, because all you need is a graph with denser parts and very sparse overall, and then you get a problem. But it leads to this definition. So let's look at all subgraphs, and let's look at the points where any subgraph appears. Let's take the worst possible case for a subgraph. The minimum P such that the expected number of copies of a subgraph is at least a half for every single subgraph. Okay, if we take that, then clearly the appearance threshold for the whole graph is at least what the worst case is for any given subgraph. And so the next guess is that the appearance threshold will be fairly close to this new thing, this expectation threshold. That works for this graph here. It's correct for that. All right, well, that guess is not one that anyone in graph theory actually made. It's just reasonable perhaps to think about it. But there's a big contradiction that Erdős and Rényi knew about. If you take a Hamilton path, so a path, that's just a path, one path that passes through all vertices. It's a path with n vertices. So the probability that, or the expectation threshold, the point where the P, such that the expected number of Hamilton paths is around a constant, is close to E over n, constant over n, but then the appearance threshold is much later. It's log n over n because you know it's at least that because you don't get, because to have a Hamilton path, every vertex has to have degree at least 1. So that's already known. In fact, the actual appearance threshold is known to be asymptotically log n over n, which is one of the big results rather earlier in random graph theory by Aitai, Komlosh and Semeredi and independently Bolabash. So we have this log n ratio there. Now at this point, I guess you might try to find what's going on with Hamilton paths, why is there a log n there, and maybe we can make a new definition and adjust for it like we did before with the expectation threshold. Well, that's not the way things went, but Kahn and Colóquio made a fairly brave conjecture that not just for like Hamilton paths and a few other things, but for any graph at all, that the maximum ratio of appearance threshold over expectation threshold is order log n. Well, log n isn't very big in the scale of things, so this, if true, would be pinning things down pretty well. It turns out that this conjecture seems to be very hard. There are some very special cases which are unsolved. For instance, for trees even, those spanning trees. It's not even known for those. When H is a spanning tree of some sort. Well, a Hamilton path is a special case of a spanning tree. It's known for that. and for those bounded degree trees which have enough leaves and so on. Even another, well, a more special case, just basically one graph for every n. Take this graph. It's a comb, so it has, well, it's called a comb because it looks like a comb. It has root n paths of length root n, basically, attached at a spine. So Kahn made a conjecture about 15, almost 20 years ago, that the threshold for the comb should also be a constant log n over n for some c. So we know that the comb won't appear until, it's got min degree 1, so it won't appear until p is basically log n over n, but so how much denser does the random graph have to get? Hopefully just a constant factor. Now this conjecture was made, but it doesn't seem to have been written down anywhere. I think it's a bit surprising given that it's been mentioned in many talks that I've been to. And I guess that the conjecture didn't get written down because no one actually got something that kind of got close to solving it. So he picked this sort of tree as something that's intermediate between something like a Hamilton path that only has 2 leaves. And if you have a tree with only a few leaves, then you can adapt existing technology to prove things about those. And it's intermediate between that and trees with constant times n leaves, for which, you know, other technologies can deal with that sort of tree. In fact, if you have constant times n leaves, the arguments are fairly simple, really. So that's the comb conjecture. And that's the end of the threshold talk. So I want to talk about random regular graphs, which we've just seen now once so far in the talk, and I'll tell you a bit about the results that are known about those and how they can be used, at least in one case. So the notation I'm using is GND for a random graph that's it's taken from all d regular graphs on n vertices. So every vertex has degree d, and the probability of each graph, the probability distribution is, the probability function is uniform. Same probability for every graph. There are lots of results known that were proved in the 80s. Now, for all of these, you know, quite a lot of information is known on how much, or what the distribution is of short cycles, for instance, and the connectivity of random d-regular graphs, and distributions of eigenvalues, and so on, and distribution of diameter. It was also shown in the 80s that these random graphs have Hamilton cycles if d is at least 800 or so, with probability tending to 1 as n goes to infinity. Now, a Hamilton cycle is one big cycle that goes through all vertices without repeating a vertex. So various people were involved in these particular results, and there were other results proved by various others as well. Oops. Now, in order to get your hands on a random regular graph, you need something. With GNP and GNM, it's obvious. You know the probability that edges occur in different places by immediate elementary considerations. For random regular graphs, it's different. And Bolabash proposed this model, which was used for many of these results here. Other results can be proved using enumeration methods or results of Bender and Canfield, but the model gives you a nice, easy way to prove things. Well, easy to start off anyway. So to demonstrate the model, this is going to be a random 3 regular graph on 6 vertices. You just start with 6 buckets of 3 dots each, and then you take a random matching up of all the dots in the buckets. Okay? Just do it uniformly at random, pair up the dots, and then treat the buckets as vertices. And that's a 3 regular graph on 6 vertices. Now, it is possible that you get multiple edges or loops, and those configurations occur with different probabilities. But if we condition on no loops or multiple edges, then we get every graph with the same probability. And people are usually interested in the graphs with no loops or multiple edges. So it's simple to see that everything has the same probability, and with a little bit more work we can check that the probability of getting no loops or multiple edges is actually a positive constant, which immediately means that if we show that a random graph generated of the sort using these dots, even if it has loops or multiple edges, just work with this model. If we show that a property holds with probability tending to 1 as n goes to infinity, then after conditioning on no loops or multiple edges, it will also tend to 1. When property tends to 1 as n goes to infinity, I say it occurs asymptotically almost surely. So Robinson and I in '94 extended the results about Hamiltonicity and showed that actually not using this configuration model initially, but maybe eventually we put things in those terms. For fixed d at least 3, you have this Hamilton cycle in a random d regular graph. Random 2 regular graphs don't have Hamilton cycles. They have lots of cycles and nothing connecting them. But with 3 regular graphs, it's just enough to make sure that with probability tending to 1, that the thing's Hamiltonian. Now, I want to mention something about the approach. I won't go into details, but a standard approach for proving things is to say, let's look at the expected number. With any luck, the expected number of these Hamilton cycles, say, goes to infinity, so there's lots of them. Well, that doesn't prove that asymptotically almost surely a graph will have one. It might be that some graphs have many, and other graphs, quite a lot of graphs, maybe have none. But the average is big. Okay, so the next step to show that it would be true that they almost all have a Hamilton cycle would be to show that the standard deviation of this counting number is very small. So if the distribution of the number of Hamilton cycles is tightly concentrated away from 0, then the probability that it's at 0 will be 0. And you can just use Chebyshev's inequality to show that it tends to 0 in that case. So that's if the standard deviation is a little lower of the expected number. It immediately follows that it almost certainly won't be 0. Well, bad luck for Hamilton cycles. The standard deviation actually is asymptotically a constant times the expected value. So it could be that quite a few of them are 0 and quite a few are bigger than the expected value. It took quite a bit to overcome that problem. Actually, Yoshi mentioned it in the introduction. It's turned into a method that does quite a few other things for random regular graphs called small subgraph conditioning, where we calculated the interactions between this random variable x and the variables that count short cycles. There's something going on there. Somehow the distribution of short cycles influences the number of these huge cycles. And basically we take account of that influence and show that asymptotically almost surely there'll be a huge cycle through all vertices. I want to mention another sort of model of not just the uniform model, because I'm going to actually use these things with this comb conjecture. So take a random Hamilton cycle, call it Hn, the space of random Hamilton cycles. Take a random perfect matching, or if you like, just a random one regular graph, it's the same thing. Now, if we superpose them one on top of the other, stick one on top of the other, so in other words, we generate them on the same vertex set. If it has no loops or multiple edges, then it's a random 3 regular graph in the normal, simple sense. What we can do is throw it away if it has any multiple edges. If the green and the purple corresponded, then we would throw it away. The probability of having a multiple edge is actually bounded away from 0. So the resulting space we call Hn plus Gn1. Now, this probability space is a bit hard to study because it's not uniform. The probability a graph occurs in here is proportional to the number of ways you can decompose it into something from Hn and something from Gn1, because we took those members uniformly at random. So it depends on how many Hamilton cycles it has. In fact, if you have a Hamilton cycle, then the rest of the graph must be a perfect matching, because it's 3 regular. So it's proportional to the number of Hamilton cycles. Okay. Now, in order to study two sorts of models, we now have this superposition model of 3 regular graphs and the uniform model. For every n, we have a probability space. Now, so we've got two sequences of probability spaces, and I'm going to say they're contiguous to each other if any event that's asymptotically almost surely true in one of them is also asymptotically almost surely true in the other, and vice versa. I wrote false, false there. If you write false, false, then that's equivalent to saying vice versa for A and B, going backwards both ways. Now, that sounds like you're demanding a lot from your two probability spaces. Every single event you can imagine that's asymptotically almost surely true in one is also in the other. But what it's really saying, it's saying that if you look at any set in one space that's of decent probability, and you look at what probability that set has in the other space, the ratio between those two is usually not very big, usually bounded by a constant. That's what this says, really. Okay. How do you prove two sequences of spaces are contiguous? Well, actually, that's what the small subgraph conditioning method does. In this case, it shows that things like this are contiguous to each other. So what we showed really was that the random three regular graph with uniform distribution is contiguous to this superposition of a Hamilton cycle plus perfect matching. Okay, now once we have that, of course, you look at the space on the right and you say, does it have a Hamilton cycle? Yes, it does, because we built it in right there. So the probability is 1 of having a Hamilton cycle there. So by contiguity, the probability is asymptotic to 1 that this thing has a Hamilton cycle. So GN3 is Hamiltonian. Okay. We also proved that you can basically add a 1 regular graph and a d minus 1 regular graph, and you get something contiguous to a d regular graph. Okay. By the same method, again, this small subgraph conditioning. Now that tells you that, well, by induction, this guy here for d at least 3 has a Hamilton cycle, so this one here has a Hamilton cycle as well, asymptotically almost surely. Now, a whole lot of people jumped on the bandwagon of this small subgraph conditioning and contiguity, and various different results, pieces were added to the puzzle, and eventually it's known that, well, more than this, but I just thought I'd state this one. So if you take any number of random Hamilton cycles and random regular graphs, put them one on top of the other, and just add up all the degrees, they're all regular graphs, add up the degrees, then throw it away if it has any multiple edges, then the result is contiguous to a random d-regular graph with the uniform distribution. There's one exception that it's not worth mentioning. For any non-trivial case, you get something contiguous. So this is a bit like sprinkling, okay? In the standard model of random graphs, GNP, you can put random graphs one on top of the other, and you can use a random part of one of them and a random part of the next one, and what you've got all together is your random GNP. So here we've got something contiguous to GND broken up into little pieces that you can do things with. Okay, so back to the comb conjecture. We're going to actually do something with this. Okay. So the comb conjecture, well, the theorem now is with Jeff Kahn and A.L. Lubetsky. We seem to have proved the comb conjecture. So remember it said that asymptotically almost surely there's a comb in GNP when P is constant log n over n for some sufficiently large C. And that was the comb. In fact, we proved more than that. We proved it for K comb. If you think of K as the length of the teeth here, then that's a root n comb, and you can do it for any other comb as well. Our method that I'm talking about today proves this whenever the teeth are lengths at least constant log n. We do have some other result that does things when K is smaller than that as well, but it's an entirely different method. So that's the theorem. Now, you might have noticed if you were malicious and you looked at this, you would say, I'm assuming that every number n has a square root that's an integer. And I'm also assuming actually that every number k divides every number n. And it's not quite like that. So what I'm doing, or what the comb conjecture says really is, take those n's for which the divisibility condition holds, And if you want to prove things like this when n is not divisible, then similar things should hold, and presumably minor modifications of the technique will do it for you. Okay, so we just have to assume n, root n is an integer. So I'm going to talk about the structure of the proof at a high level because it uses some of the things I've been talking about. What we do is we start with GNP. We're going to try to find a comb in GNP. It's a spanning subgraph. It uses all the vertices. That's the hard thing, really. So we break it up. We use this sprinkling. We let P1 be very small, constant over n, and P2 and P3 around log n over n. They're just a little bit above log n over n. P2 and P3 are such that we know actually the minimum degree in a GNP2 or a P3 is actually very large. And then we sprinkle them one on top of the other, sprinkle the edges of each one, or take the 3-round exposure. So we get a GNP where P is at most constant log n over n. And we're going to be able to use the independence of these 3 graphs. They're all independent because they just come from independent random graphs. So the first thing we do, in the first random graph, it has constant over n vertices where the constant is bigger than 1. Now that means, if you think back to the phase transition part of this talk, there's already a giant component in GNP1. There's a giant component and it's got a giant kernel and there are long paths in there. We can certainly find a path of root n vertices. It was proved a long time ago by Semerady and others that actually you can find a path of length constant times n in GNP1. So we can find this path there. Let's put the path of root n vertices there and let's look at all the other vertices in the graph. Now these 3 graphs have the same vertex set. Okay, we can find a Hamilton cycle in G2 because in the remaining vertices of G2 because that's going to be a random graph GNP where the P is just big enough to find a Hamilton cycle by the threshold result we know about Hamilton cycles. So you find that graph just using the edges in here, and then you find a matching, what's called a perfect matching of those vertices in the 3rd random graph, using again another result, actually one from Erdos and Rainey back in the 60s. That graph is dense enough to find a perfect matching, with probability tending to 1 as n goes to infinity. All right, so we found those 3 things. Now if this button would work. Okay, the next thing we do is we find in that we had a perfect matching plus Hamilton cycle. Now they're both random, so it's a random superposition. So in that random superposition of h plus m, by contiguity we can look instead in a random 3-regular graph and find what's called a k-cycle factor, which is a set of cycles of length k covering all the vertices. Now, the fact that we can find that was something that wasn't known already. We can find it with probability tending to 1. Now, the last thing to do, by yet another old result of Erdos and Rainey, which I'd call bipartite matching, we can look in the edges of G2 and G3, joining these things, okay, joining that path to these cycles, and we can match each path vertex to a cycle. It's a sort of a bipartite matching result, and these things exist by a result in yet another paper of Erdos and Rainey, which I haven't mentioned, that's in the 60s. Okay, at the end you break the cycles like this, and now what you see is a comb that's gone all curly. Okay, it's actually the comb that we were after. So that's how it works. Now actually everything in that proof is entirely straightforward, except for one thing that occupied about 98% of our time, which has been considerable, which is showing that a k-cycle factor exists in this random 3-regular graph that was there. And actually to do that we ended up getting into things, and we have to prove or sharpen results that are known in renewal theory and prove that they're uniformly valid and all sorts of things. And there's no time to talk about any of that. but that was the hard bit anyway. Now, I want to say that I've already used contiguity here in this proof, but in order to prove the k-cycle factor as this, then the basics of the argument was the old Hamilton cycle argument. In other words, we're again proving a contiguity and using small subgraph conditioning. So it came into the proof once more. Okay, so that's the summary of the proof of the comb conjecture. You see the comb does exist in this random graph, and that leaves us basically in the dark. Well, I want to say we're still in the dark about a lot of things. There are plenty of trees left. Okay. The comb was meant to be, I'm not sure I haven't asked Jeff Kahn how he feels about this, but I think the comb was meant to be one of those typical things, and maybe if we did this, we get a new technique, right? And to some extent that's true, but probably less than he hoped. I'm not sure, I guess. You see, some other non-comb trees are covered by a method. A trivial thing you can do is break the cycles in different places. But there are a number of other ways you can adjust what we've done to get a variety of trees, and I guess we still haven't looked hard enough to see whether we can get all the trees that are remaining, but we kind of gave up more or less that approach. So there are minor modifications, but many trees remain about which the tree conjecture is unsolved. We want to find the threshold of these trees, at least within the constant factor. Of course, once you pass from trees, there's all the other graphs in the world are still out there, almost all of them. In some sense. There are many cases where the Kahn-Collow conjecture is unsolved. Is there this log n ratio between appearance thresholds and the point where your expected number of subgraphs is at least 1 or a half? And I just wanted to mention too that of the other things I've mentioned, the superposition stuff I think is useful and interesting, and it's a pity that we can't prove that you can't do more superpositions. If you superpose many graphs one on top of the other, not just a constant number, suppose you take d copies of a random one regular graph, where d is growing like log n or root n. It should, for the first one here, it's extremely safe to say that this will be contiguous to a random d regular graph, but the methods just don't seem to work. We seem to need a new method. So I'll finish this talk with a ... Thanks.